Hello everyone, my name is Vijay Kumar and we are studying refrigeration and air conditioning. In the last video, we have seen one question that was based on ideal reverse Brayton cycle. That was question number 1. Now we will see question number 2 that is based on actual reverse Brayton cycle. Let's see the question. Let's see the second question. A dense air refrigeration cycle operates between pressure of 4 bar and 16 bar. The air temperature after heat rejection to the surrounding is 37 degrees Celsius. And air temperature at exit of refrigerator is 7 degrees Celsius. The isentropic efficiency of turbine and compressor are 0.85 and 0.8 respectively. Determine the compressor and turbine work and COP. Given is you have to take gamma is equal to 1.4 and coefficient and CP specific heat is 1.005 kilojoule per kg Kelvin. So let's draw the given value on TS diagram. You know very well that this is the TS diagram. Okay, this is the 1, 2, 3, 4. This is the ideal reverse Brayton cycle. You know very well this thing. Here you have given the efficiency 0.85 and 0.8 for isentropic efficiency of turbine and compressor. So this is compressor. If isentropic efficiency is given, that means this will not be the actual process. Actual process will be adiabatic process that I have explained in my previous video. So this will be the actual process 1 to 2 dash. Okay. Now in the same way, the expansion processes have the isentropic efficiency 0.85. Isentropic efficiency of turbine or expansion process have 0.85. So the process will occur like this. Okay, this will be the 4 dash. So 1 to 2 dash and 3 to 4 dash is the actual process. Okay. Now, what are the values there given? You see here, in a dense refrigeration cycle operates between pressure of 4 bar. So this is pressure P1 is equal to 4 bar and 16 bar. So this is P2 is equal to 16 bar. Now the air temperature after heat rejection to the surrounding is 37 degrees Celsius. That means 2 dash to 3. This is the process for heat rejection. So the temperature at the exit of heat rejection is 37. That means 3. That means T3. T3 is 37 degrees Celsius. You write here on this. T3 is equal to 37 degrees Celsius. Now you have to convert it into Kelvin. So 273. We will add 273, then it will become Kelvin. Okay. Now what will be the T3? 73, 10, 1, 3. 310 Kelvin. Okay, this is the T3. Now air temperature at the exit of refrigerator is 7 degrees Celsius. And which one is the refrigerator process or cooling process or heat addition process? That is 4 dash to 1. So at exit of the refrigerator temperature is 7 degrees. That means 1. 1 is the exit of the refrigerator. You know this process is the 4 dash to 1. This is process of refrigerator. So T1 will be, so directly I will calculate in Kelvin. 7 plus 273. This will be 280 Kelvin. Okay. Now all the values I have given here, gamma we know and Cp we know. Now we will find out all the other parameters like 4 dash, 3 and 2 dash. We don't know all these values. So how we will calculate? We will calculate by the process of isentropic compression and adiabatic compression. That means isentropic efficiency of turbine and isentropic efficiency of compressor. So first we will take the isentropic efficiency of isentropic efficiency of compressor. 1 to 2 and 1 to 2 dash. So isentropic efficiency of compressor. Isentropic efficiency of compressor. You know, isentropic efficiency of compressor is, I have already told that less by more. Remember, less by more. In which process we are giving less input, less work input, in which we are giving 1 to 2, we are giving less work. So T2 minus T1 divided by T2 dash minus T1. So we know T1, but we don't know T2 and T2 dash. We don't know T2 and T2 dash. How we will calculate? And the efficiency of isentropic efficiency of compressor we know. So we will calculate T2 and T2 dash. How? You will see here. You know that process 1 to 2 is a reversible adiabatic process or isentropic process. Okay, for isentropic process and reversible adiabatic process, you know the equation. What is that? P2 by P1 is equal to P2 by P1 to the power gamma minus 1 upon the gamma. So you can calculate T2 from here. T1 you know, P2 you know, P1 you know, gamma you know. So T2 divided by T1, T1 is 280 Kelvin. P2 you know, what is P2? That is 60. P1 you know, 4 to the power 1.4 minus 1 divided by 1.4. Because gamma is given 1.4. Now T2 you can calculate. T2 is equal to 280 into, this is 4 to the power 0.4 divided by 1.4. So you can calculate through the calculator. What will be the value? Calculate 4 to the power 0.4 divided by 1.4. You keep this value in bracket during the calculation in calculator. So you will get 1.4859 means 280 into 1.486, because value will be 1.48489. So for round off I will take it as 6. Okay, this will be 6. I have written 1.486. Now multiply this with the 280. You got T2 is equal to 416.07 Kelvin. This is 1.486 and this is 416.07 Kelvin. You can write here. Now you got T2. You have to calculate T2 dash. How you will calculate? You know efficiency of compressor. T2 you have calculated. T1 we know, and T2 dash we can calculate from here. Now So whatever the values I have calculated, I have written here. T3 is equal to T10 Kelvin, T1 20 Kelvin, and T2 416 Kelvin. I have round off this one, so it will be 416 Kelvin, 416 Kelvin. Okay. Now I have to calculate T2 dash. So we will put all these value in this equation. Efficiency of compressor, we know 0.8 it is given, and T2 you have calculated 416 Kelvin. Okay, don't write Kelvin here directly because it is in plus minus case. 416 Kelvin, then T1 you know 280 Kelvin divided by T2 dash. T2 dash we have to find out minus T1. T1 is 280. So what will be T2 dash? I'll directly calculate through the calculator. 416 minus 280 divided 0.8 plus 450 Kelvin. 450 Kelvin. So we got T2 dash also 450 Kelvin. Okay. Now I will write here T2 dash also. T2 dash is equal to 450 Kelvin. So you know T1, T2, T2 dash. Now in the same way we will calculate T3, T3 you know. T3 you know T10 310 Kelvin. So T4 and T4 dash we will calculate. Okay. Now we will calculate T4 and T4 dash. You know 3 to 4 process is a reversible adiabatic process or isentropic process. So you know the equation T3 divided by T4 is equal to the same way 16 divided by 4 I write directly, then 1.4 minus 1 divided by 1.4, gamma minus 1 upon gamma. Okay. So T3 is 310 Kelvin divided by T4, that will be 4 to the power 0.4 divided by 1.4. So through calculator we will find out here 4 to the power, keep this value in bracket and during the calculation in calculator 0.4 divided 1.4 again, this we got 1.485. 1.485. So T4 we can calculate. T4 is equal to 310 divided by 1.485. So what will be the value of T4? 310 divided by answer. That is 208.6 Kelvin. So we got T4. Now we have calculated T4. We will write here T4 is equal to 208.6 Kelvin. Okay. Now I have to calculate 4 dash also. What will be 4 dash? We'll see here. You know 3 to 4 or 3 to 4 dash is a process which is going on in the expander or turbine. So you know the efficiency of turbine, that is, I'll write directly less by more. Remember again, less by more. In which process I am getting more work output? In this case, I am getting less and more work output. So 3 to 4 I am getting less work. That means T3 minus T4. And from 4 dash, because this is the less work now. If I write like this, in which process I am getting less work? 3 to 4 dash. So T3 minus T4 dash divided by T3 minus P4. Okay. Efficiency of turbine, you know, 0.85 is equal to T3, 310 Kelvin minus T4 dash I have to calculate divided by T3, 310 Kelvin minus T4. T4 we have calculated 208.6 Kelvin. Okay. So by calculation of all these of this equation, we will get T4 dash is equal to 223.8 Kelvin. Okay. So I'll write here T4 dash is equal to 223.8. Okay, friends. Now I think we got all the temperature values. So by putting all these temperature values in compressor and turbine work and COP, we can calculate. Okay, let's see. Now, what is the compressor work? You know, formula for compressor work is mass flow rate of refrigerator into Cp into change in temperature. Compressor work T2 dash minus T1. T2 dash minus T1. Because here efficiency is given. Efficiency is given for compressor or turbine, you remember, always take actual work 1 to 2 dash. Okay. So now you can see here Cp is given, T2 dash is we have calculated, T1 also we have calculated. But what about mass flow rate? That is mass flow rate m dot. How you will calculate here? You will see here. Now how you will calculate mass flow rate? If it is not given in question, you have to calculate by the formula you know. 1 TR. 1 TR is equal to 210 kilojoule per minute. You know what is this? This is refrigeration effect. This is refrigeration effect. That means 1 TR is equal to 210 kilojoule per minute is a refrigeration effect or refrigeration process. And which one is the refrigeration process? 4 to 1. You know 4 dash T temperature at 4 dash and you know T1 also. So we will calculate this like this. Refrigeration effect in this case. What is refrigeration effect? Mass flow rate into Cp into T1 minus T4 dash. So Cp you know, T1 you know, T4 dash you know. But RE is this one, 1 TR. Suppose it is given in question that determine the compressor and turbine work per TR, then you know very well it is 1 TR. But if it is not given in the question, then you have to remember that you have to take 1 TR is equal to 210 kilojoule per minute. In that case, sometimes examiner asks directly, sometimes examiner gives the value here. So in this case, I have not given the value. So you have to think that 1 TR is equal to 210 kilojoule per minute. So you put the value of RE 210 kilojoule per minute is equal to mass flow rate. You know Cp is given 1.005 into T1. T1 is 280 Kelvin minus T4 dash. T4 dash is 223 minus 8. 223.8 Kelvin. 223.8 Kelvin. So from this you can calculate easily mass flow rate. Then mass flow rate will come by calculator. If you calculate the value 280 minus 223.8 multiply 1.005. This will be 210 divided by, I have calculated this value, and this is 56.481 in the calculator. So 210 divided by answer, I'll get 3.718. We have calculated, it has come 3.718 or 3.72. This will be in kilogram per minute, kg per minute. I have got mass flow rate in 3.72 kilogram per minute. Okay. Now, to calculate the compressor work, so mass flow rate I have calculated. This is 3.72 kg per minute. 3.72 into Cp, you know, 1.005. T2 dash is 450 Kelvin minus T1 is 280 Kelvin. Okay, if I calculate here WC through the calculator, I will directly, that you can easily calculate, this will be 635.6 kilojoule per minute. Okay friends. Okay, this will be the work done through a compressor. Remember one more thing here. You have calculated this work done per TR. This is the per TR work done. Per TR. Why? Because in question nothing was given. In that case you have to think. If it is given, you have to calculate per TR. Then you get it is already given. And if maybe you have to. Maybe in question mass flow rate is given, then you have to put the value of mass flow rate directly here. So there are different types of questions. So we have calculated work input to the compressor per TR. Okay, now we will calculate the work done through the turbine or work output from the turbine. Okay. So what is the work output from the turbine? That will be, again, it is mass flow rate into Cp into changing temperature. What is the temperature? Actual temperature. T3 minus T4 dash. Okay, mass flow rate is, you know, 3.72. Cp, you know, 1.005. Then T3, you know, 310 Kelvin minus T4 dash 223.8. Okay. If directly I calculate, you can calculate through the calculator. What will you get? You will get 322.3 kilojoule per minute. This is also per TR. This is also per TR. Now we will find out the coefficient of performance for this cycle. You know very well the COP for reverse Brayton cycle. So you know the COP is equal to 1 divided by RP to the power gamma minus 1 upon gamma minus 1. You can easily put the value RP, gamma, and you will get the COP. Whether it is correct? No. This formula will not work here. I have already told that this formula is for ideal reverse Brayton cycle. That means process 1, 2 and 3, 4. If process 1, 2 and 3, 4 are involved in a cycle, then this formula will be used. But here, actual process is 1 to 2 dash and 3 to 4 dash. So we will use the formula for COP. Basic formula in my first video I have explained. What is COP? COP is ratio of refrigeration effect divided by W net input. W net input. So friends, RE you can easily Find out here MCP T1 minus T4 dash, and W net input means it is the minus of WC and WT. Okay, net work input we will calculate from this, and RE we can calculate for this process. Okay, so COP will be RE. RE will be the refrigeration effect, means mass flow rate into Cp into T1 minus T4 dash divided by net work. That will be minus WC, because it is minus plus WT. This will be the net work. If I put all these value, mass flow rate is 3.72. 3.72 into 1.005 into T1. T1 is 280 Kelvin minus T4 dash. T4 dash is 223.8 Kelvin divided by minus WC, means this is 635.6 plus WT 322.3. So after calculating this, you will get the answer COP 0.67. 0.67. This will be the COP. Okay. Now you have to remember some little points here, that while I have taken minus is work input to the compressor, plus here work output from the turbine. So the net work will be we will calculate by this. Okay, I have already told in the previous video. One more thing, whether I am given this value, you can easily say that this is the 210 kilojoule per minute. You will calculate this, because during the calculation of, or during the finding out of mass flow rate, we have considered refrigeration effect 1 TR. 1 TR we have considered. Okay, you can put 210 divided by this value, you will get again the same value here. Okay, by this you can calculate, or you stick to the basic formula, mass into Cp into delta T. Okay, so this is the COPO reverse Brayton cycle. So friends, in this video we have seen one questions of actual reverse Brayton cycle. In the next video we will see the application of reverse Brayton cycle. In that we will see the aircraft refrigeration system. One by one we will see all the processes and all the systems of aircraft refrigeration system. Okay, thanks for watching and have a good day.